So Claude Shannon had defined the channel capacity as an upper bound for all achievable rates. This is your rate of transmission, right? And this is your capacity. The capacity is an upper bound at which you can transmit information reliably over a communication channel. So let's say you're trying to encode let's say this message is S, right? And you've got a certain encoder encoding it as X, right? Then you've got your channel that, introduces a bit of ambiguity on X. And this channel is described by a probability density function, PDF, which is actually a conditional one. So P of Y given X, and you receive Y. By the way, X and Y are random variables, okay? You receive Y, and you've got the decoder that tries to decode this guy right here. So you get an S hat, right? We're actually concerned in this block today when speaking about the channel capacity. Let's say we're in a discrete case, right? Just to make things simple. Whereas we both know that X and Y could well take continuous values. But let's say for the moment we define them to be discrete. That is, my X line in a certain code book. So X1, that's one of them. X2 down till Xn. And likewise, I've got Y1, Y2 down till Ym. Since we just talked about a probability conditional PDF, conditional probability distribution function, then we've got to assign those probabilities as transitions, right? So we've got this guy, let's call it P11, this guy, let's call it P12, and all the way down to this guy, which is P1M, right? Same thing here, we've got P21, P22, down to P2M, and Pn1, Pn2, down to a Pnn. I know it's getting messy, I'm sorry about that. But so instead of all this, we can say in one expression, I've got my Pij, which is the probability that y takes the value yi, given that x takes the value xj, right? A very simple application on this would be the binary symmetric channel. So you've got 0, and you've got 1, and you've got 0 here, and you've got 1 here. So I'm just transmitting 1 bit. So my code book contains 1 bit. Actually, this is called a noiseless binary channel, which is a particular instance of the binary symmetric channel. In this case, you're always sure that you're going to receive the correct bit. So there's no ambiguity on the channel. The channel is identity, right? What goes in comes out. But that's not the case in real life. So that's why we've got this binary symmetric channel, which, the 0 could be received as a 1 and a 1 could be received as a 0 with a probability of error p, right? And so here I've got 1 minus p. So the probability that I do a mistake, I receive a 0, whereas I have transmitted a 1, and vice versa, when I have received a 1, whereas I have transmitted a 0, is lowercase p. And the probability of success, I transmit and receive a 0, and I transmit and receive a 1, is 1 minus p. This is what people call, in information theory, BSC, which stands for binary symmetric channel. This is one type of discrete memoryless channel, which is this guy right here. This guy, the general case, of course, this is the general case. It's called the discrete memoryless channel. And why is it? It's discrete because we just said x takes on a finite number of values, actually n values, which lie in a code book. And m takes on m values, which lie in a code book. Memoryless because when I perform this transmission again, that is at time t, I transmit s, I receive s hat, or I transmit x and I receive y. This transmission doesn't depend on time t plus 1, whereas in reality we have cases that do. So for simplicity, we have this discrete memoryless channel. I say for simplicity, but of course it's not simple. So here's a bit of context behind why we have, why we define a channel, what different types of channels we have. I also want to tell you that since x and y are random variables, then it makes sense to define, just like we do with, joint probability distributions and stuff, to model the correlations or dependencies of x on y or y on x. There's also one very important metric, okay? One very, very important metric called the mutual information. And this is a very powerful measure. It's defined as follows. So the mutual information between x and y is the sum over I and over j of xj pij log to base 2 pij over sum xk pik, and the sum is over k, where my j is the probability of the PDF of x, that is probability that x is equal to xj. Okay. Actually, you know what? Just to have some, just to be consistent, I'll call those guys, and it really doesn't matter. This is just notation. 1, 2, down till n. Let's say those are the discrete values x can take, and likewise for y, we'll say again these values are are just values. We don't care. It's the probability that counts. But just here, I didn't want to confuse the notation and have, xj twice. So this guy, I'll remove it and I'll just say, j. Okay. So this is the mutual information, and it actually measures the amount of information obtained from one random variable by looking at the other. It's that powerful. It tells you how much information you could extract. So it measures the amount of bits you can get from x by observing y. Okay. You see, there's many different expressions. In our case, this is the expression, but in general, you could verify that it is the sum over x and y, the joint PDF. Okay. Then you've got the log, then you've got the joint again, then you've got each random variable right here. You could start seeing that when x and y are independent, that means this guy could be written as a product of each PDF. That is, it's px times py. So this guy cancels with this guy. You get a log 1, which is 0. So in case of independence, mutual information is 0. You cannot extract any information from one about the other. In general, this is the formula, and we have just applied this formula right here. If you go on the web, if you go, let's say, to Wikipedia or any other, reliable source, you could check that the mutual information is also expressed as a function of so-called Kullback-Leibler divergence. So today we're interested in this expression right here. This is what we're going to be using for our capacity convex optimization formulation. Now that we've got the mutual information, we can define the so-called capacity, which is the supremum over all PDFs of x of the mutual information. And so, in convex optimization or in mathematical optimization, you can solve this problem, or can you formulate the capacity of any channel using a optimization problem. And when I say an optimization problem, I mean you could maximize the ixy expression over x. When I say x vector, I mean all the probabilities of x. So x1 down till xm. Okay? So we can just plug here the expression and we can maximize. But that's incomplete because we still need some constraints so that we're sure we're maximizing over a PDF and not something random, right? In other words, we want to make sure that the x we optimize over, that we find using this problem, is a PDF, that is, it sums up to 1, right? We want that, that's 1. And 2, this is still not complete because you could sum up to 1 but have negative values, whereas in probability we don't have negative values. So for that, we have to make sure that each xk is positive. Okay, for all k going from 1 till m, right? This could be expressed, so equivalently you can write this problem as, again, nothing has changed in the cost function, but we could express this in matrix form or vector form, where I've got the vector 1 transpose x is 1, and this is the one vector, and x is entry-wise positive. Okay? Now, let's replace the cost function here. That is, I'm going to replace this guy in the cost. We get, let's call this guy f0 of x instead of ixy, just to, stay consistent with our convex optimization course. So I and j, xj, pij, log pij over sum p, xk, pik, right? Subject to x entry-wise positive and 1 transpose x is 1. Now, this is still a bit nasty, and we could rearrange it and make it look better. And when I say nasty, I mean, you want to have an idea which one is a linear term, which one is a logarithmic term, and so on. And it's still not super clear. So what we can do is, using log a over b is log a minus log b, we could express this summation as xj pij log pij minus double sum again xj pij log, let me make some space, summation of xk pik, right? Now the first term we can write it as such, so summation over j, xj. I'm just flipping the summations and extracting outside what doesn't depend on the other. So here it's xj, and then I've got I, pij, log, pij. This guy, we can denote it by cj, right? And then in the which we could write as summation of cj, xj, or c transpose x, where c is C1 down till Cm, right? This is for the first term. Now the second term, we can do a similar trick. That is, we've got the sum outside on I, okay. Note that this term doesn't depend on j, right? It does not have any indices on j. So we can throw the log outside as such, log summation over k, xk, pik, and then I've got a summation on j, that is xj, pij. So what's left, right? Which could be written as, if we denote by yi, so letting yi is x summation over j, xj, pij, we get log yi multiplied by yi. Or in other words, we get yi log yi, which is the entropy on y, okay? So all in all, we get this term right here. Let me rewrite this, which is f0 of x, that is c transpose x minus summation yi log yi, okay? So rewriting the optimization problem we had, we would like to maximize over x f0 of x, which is also the mutual information, which is c transpose x minus the summation over yi log yi, subject to the same constraints, that is x entry-wise positive and 1 transpose x is 1, but there's something missing because we had introduced y. So we had said that yi is summation over j, pij, xj, which is, like we're saying, this guy is pi transpose x, where pi is a certain vector. Or in matrix form, if I want to stack all my y's, then we get a y equal px, is the matrix of transitions. That is, it's the matrix where its ijth entry is pij, which we had defined right here, okay? This is our matrix B. So we have to enforce this into the constraints of our problem. That is, we have to go ahead and say y is equal to px, so that we're complete, right? So this is the problem that we have, right? As you can see, this is a maximization of a certain cost. This one is affine, and this term, including the minus, is the entropy, which is concave. So the entire thing is concave. We're maximizing a concave function, that is, we're minimizing a convex function. So we're minimizing a convex function subject to some linear and an inequality constraint, That is, we do have a convex optimization problem in hand. Okay. Now this is the primal problem, and I will get back to the dual problem. I just want to show you how we could tackle these type of problems on MATLAB. So I had a video in the past. I will be linking it down in the description section below on how to use the CVX toolbox built by Michael Grant and Stephen Boyd on how to solve the water filling problem in wireless communications. So here's another chance where we will be using the CVX toolbox to solve the channel capacity problem. So let's start by downloading CVX from the official website, cvxr.com. And since I'm running on a Mac, I'll just get the standard bundle for Mac, this zip file. Wait for it to download. Once done, open it. And now I have the bundle here. I'll just add this to path and I'll cd into that. Then I'll run cvx setup. Give it a bit of time. It's done. Go back. And to make sure it's properly installed, there's this examples document. Just add this to the path and run a simple linear program, which is this. And there you go, it runs, so all is good. Now I'll remove that from path and I'll start with my main to actually code this problem in CVX. Well, first thing we need our P matrix, right? And I'll start by defining a simple P matrix. Well, in general, it's if you want to randomize stuff, you've got m by n, and then you could then divide by the rows. Okay, so let's say m is 4 and n is 3. You get such a matrix of probabilities, right? They're random. And the sum of the columns is 1, which translates into a transition matrix. But, you know, let's say I want something really simple. So this is random transition. And I want something really simple, let's say a binary symmetric channel. Okay, I'll have something like 1 minus p, p and p, 1 minus p. So it's actually what we had defined right here, no? This is the matrix we're targeting. Okay, where my lowercase p is, let's set it to something like 0.1. So every CVX problem starts with a CVX begin and ends with a CVX end, right? Over here, you'd want to define your variable, x of dimensions n by 1, right? And you want to maximize C transpose x, so we've got this C transpose x, right? Minus the, or plus the entropy, right? So we can do something like plus the sum of entropy. So ENTR is a CVX function, which stands for the entropy. I'll divide by log 2 so that I've got my logs in base 2. And now I can pass the constraints, x positive, so I'll do x entry-wise positive. And 1 transpose x is 1, which translates to sum of x equal to 1. And I forgot to define c, which was actually pij log pij, right? So in matrix form, it could be something like this, p log 2p as such. And right here, we could say y equal p times x, right? Run this. Oh, I think c should be c is a row vector. I think it should be a column vector, if I'm not mistaken. So, and y, oh, sometimes it happens that you have to define this guy before calling the problem, because x is defined, no problem, but y is not, so define it here, and there you go. So here's your capacity. So my capacity from the primal problem, which is the capacity, is cvx underscore opt val. There you go. It's 0.53. Now I want to argue some stuff here. Actually, there's something really nice here. And I want to tell you what it is. If you're in information theory and you already have the basics of information theory, you probably know this, but in case you're only into optimization and have no background whatsoever in information theory, I think you might find this interesting. So what I want to do here is do a loop, okay, of all possible p's, lowercase p's, p going from 0 till, let's take steps of 0.01 to 1, and let's call this my p axis, right? And I'll loop over all possible p's. So my loop is here actually, p axis, and I'll end here. And what else do I need to do? Actually, let me do steps of 0.1 so that we have a faster response. And let's count each time we finish. Okay, initialize it to 1 and save this guy in K. Okay, let's run this. And it's better to start with something really small, epsilon, instead of 0. Okay, and here I'm going to do a 1 minus epsilon. You know, because this, it's part of what I'm going to show you. What we're trying to optimize gives some, you know, NaN or infinity values at 0 and 1. Okay, and let me plot now p-axis versus, or C primal versus p-axis. And this is what we get. Actually, let me go a bit, let me solve this multiple times. So let's do 0.05 or 0.025, okay? And let's give this a bit of time. Let me plot this. This is what we get. So this is the primal solution versus P. It's actually, let me do this here. This is what you get. The capacity versus P. And it has a very convex shape, right? And let's try to interpret the result. At P equal to 0.5, the capacity is 0. It means that you cannot reliably transmit over this type of channel when P is 0.5. However, when you start approaching the edges, 0 or 1, means you can transmit at 1 bit per second with vanishing probability of error. At P equals 0 means that we have no probability of error. And so every time we receive something, we can easily identify what has been transmitted, right? When I receive y equal to 0, I can easily say my x is 0. And likewise, when y is 1, I can easily say that x is 1 without any sophisticated, you know, decoders or stuff of that sort. Likewise, when the probability of error is 1, and even though that's counterintuitive, your data rate is also 1 bit per second, because when you receive y equal to 0, you know you have a very bad channel, and so you can say, oh, my x is the inverse, so it's 1. And likewise, when you receive y equal to 1, again, since you have a very bad channel, you could say my x is 0, right? So it's also very reliable. Okay, now when P is 0.5, you're midway. Whether you receive a y equals 0 or 1, you can never be so sure about what has been transmitted. And that's why your capacity is 0 bits per second. And the reason I had plotted this is to show you that we actually know the solution. And what is the solution? It's the following. So I'll hold on and I'll do 1 minus P times log P minus, I think it was a 1 minus P, and I'll plot this guy in red. And if I evaluate only this block, oh sorry, my p-axis is uppercase. Oh, it should be the inverse. I'm sorry about that. So this guy is a plus. Right, so you can see that the blue and the red are coinciding with each other. You don't believe me? You do this. And there you go. The red and the blue actually coincide with each other. And that's why, as I said, we know the solution. And it's the 1 minus entropy of P. And this is pretty classical in information theory for the case of binary symmetric channels. Okay, so that's good. You can actually solve, without the knowledge of some results in information theory, any channel you want. Okay, using this optimization problem that you have here. Now, another interesting thing that I want to tell you about is the dual problem. So in case you've been watching my convex optimization lectures, For each primal problem, so for each original problem that we have, we can formulate the dual problem. And that is very fascinating because the dual problem is sometimes easier to solve than the primal problem. However, it would be optimal if the duality gap is 0, right? So you would instead solve another problem, which is the Lagrangian dual function. You'd maximize the Lagrangian dual function, okay? Subject to just a positivity constraint on lambda, which is the Lagrangian multiplier on inequality constraints. You would solve that problem, and if duality gap is 0 for convex optimization problems, if KKT conditions are satisfied, then you'd have strong duality. So let's see what we get over here. So I'm going to rewrite this problem as a minimize first of all. So instead, I'll minimize the negation of the cost function that I had. So minimize minus C transpose X plus summation of yi log yi, subject to same exact constraints. That is X positive, 1 transpose X is 1, and y equal px. And I just want to tell you something here. Before I go ahead and write the Lagrangian dual function, I want to show you a section in Boyd and Vandenberghe's convex optimization book where we actually have an expression. Let's say I have the following classical convex optimization problem, okay? I'm minimizing f0 of x, right? Subject to ax less than b and cx equal to d. Then my Lagrangian dual function, which is the infimum of the Lagrangian of the problem over x, so it's the infimum of Lx lambda nu minus, we can actually show that this is minus b transpose lambda minus d transpose nu minus f0 conjugate, it's the conjugate function of the cost function that we have, of minus a transpose lambda minus c transpose nu. Okay, so the dual function would actually be, for this primal problem, we'd have the dual problem of maximize minus b transpose lambda minus d transpose nu minus f0 conjugate of minus a transpose lambda minus c transpose nu. Okay, subject to lambda entry-wise positive. Okay, so all we have to do to formulate this problem is to identify our a, b, c, and d, and most importantly, the conjugate function. If we can do that, then we're done. We have the dual problem. Okay, and I want to tell you about something, is that let's try to absorb this constraint within the problem, so that we can have our problem in one of the variables, right? That is, we always want this constraint to be satisfied, y equal to px. It's a critical constraint. You always want to have that. The probability, the PDF on y is the conditional probability of y given x times the probability on x. But let's try to instead replace x is p pseudo inverse y. Since we've got the y log y and we already know the conjugate of this guy, let's keep it clean and replace x with p pseudo inverse y and see what we get. So for the time being, let me copy paste the cost that I had, which is, let's call it PC, that is P for capacity, the primal problem of capacity. It is minimized with respect to x, C transpose x. So I can write this guy under some certain conditions. The x is P pseudo inverse y. And let's replace it here, here, and here. Okay, let's see what we get. So by doing that, now the minimization is over y, right? We get C transpose P pseudo inverse y minus yi log yi, and subject to p pseudo inverse y entry-wise positive. And that does not mean that y is entry-wise positive. If I put y as entry-wise positive, it doesn't imply that p pseudo inverse y is entry-wise positive, because p pseudo inverse could have negative values. And 1 transpose P pseudo inverse y is 1. And I can actually do this, call this C bar transpose, where C bar is P pseudo inverse all transpose times C. Okay? So looking at this and this, I could identify my A, B, C, D, and F0, right? So if I would match both optimization problems, my F0 of X, or in this case Y, right, is C bar transpose Y minus yi log yi. My A is minus P pseudo inverse. My B is 0. My C is 1 transpose pseudo inverse, right? This is C and this is D. D is 1. Not the vector 1, but the scalar 1. Okay? Now, as you can see, we've got everything. We've got my D transpose nu, my B transpose lambda. We need the conjugate of F0. And thanks to writing it in this form, this is easily achieved. How can we do that? Well, it's super easy. Since my F0 of y is minus C bar transpose y plus sum of I yi log yi, which I can write as an entire sum of minus C bar I yi plus yi log yi as such, where C bar I is the ith entry of C bar. Since I have it in that form, we're almost done. Why? Because we already know the conjugate function of this guy. And what is it? The conjugate function of yi log yi is EYI star minus 1. Okay? And what is yi star? It's the variable of the conjugate function. So if I have, in other words, if I have g of y, which is y log y, where y is a scalar, then g star of y star is e y star minus 1. Okay, we have this term. And we also know that, I'll point this out in Wikipedia, because here's a table of selected convex conjugate. Oh, by the way, the conjugate function is also referred to as convex conjugate, or Legendre transforms, or also the Fenchel transforms, something like that. So we also know that if we do this type of combination right here, we get this. What we have is alpha equal to 0, beta is minus ci, gamma is 1, lambda is 1, and delta is 0. So plugging this all here, what we will get is f star x star minus beta, because alpha is 0, delta is 0, so we don't have those first two terms. And what I have is also gamma is 1, gamma and lambda are 1, and so I get a shifted version of my conjugate function, right? And by how much is it shifted? By minus beta, where beta is minus ci, right? So applying this here, if I have my gy is y log y, then my minus ci bar yi plus gy would give me a conjugate transform of g star y plus y star plus, this is yi star in case we want to remain consistent, plus ci, which is exponential of y star plus ci minus 1. So in that case, I get that my f0 of y, which is nothing other but the summation of this term right here, minus ci yi plus gyi, then my f0 star y star is the summation over I of EYI star plus CI minus 1. Now, I did something here without saying why. I used the fact that the sum of functions will give you the sum of conjugate functions without saying why. It happens to be true in this case only because each term in the sum, which is minus CIYI plus GYI, right? Each one in this term is independent from the other. So each one depends on yi and not yi and yi minus 1, or any random combination of two yi's, yi and yj, for example, right? So you can only say this when you have each term in your sum independent from the other in terms of the variables within the cost function, right? So good. Now we have the expression. Now we have the conjugate function. All what remains to do is to plug this form inside, right? So using this dual optimization problem right here, what I get is to maximize, go back up, we've got that the first term is minus b transpose lambda, where b is 0, so I don't have that. And we have a minus d transpose nu, where d is a scalar 1, so I get only minus nu. So minus nu. Then I've got the minus conjugate function of this composition, right? So I get a minus sum of exponentials because of this term right here. And my yi star is actually the ith entry of what I have in the argument. So it's the ith entry of minus A transpose lambda minus C transpose nu. And actually, and this is the matrix C and not the vector C, okay? Just in order to avoid confusion. So it's the ith entry of this guy. And I can also express this in vector form as EI transpose multiplied by minus A transpose lambda minus C transpose nu. So my A is minus P pseudo inverse. So I get that from here. Yi star is EI transpose P pseudo inverse multiplied by lambda. And I have a minus C transpose nu, where C is 1 transpose pseudo inverse. So that means my C transpose is P pseudo inverse transpose 1 vector times nu. And that's it. So I'll plug this guy here to get what I have in my exponent here, right? So that means that I get an EI transpose P pseudo inverse lambda minus P pseudo inverse transpose 1 nu, 1 vector nu, plus Ci bar, oh, by the way, this is Ci bar, I'm sorry. So Ci bar minus 1, okay? Subject to a positivity constraint on lambda, right? And to have a cleaner, dual function, I can do this. So I can do maximize minus nu minus I exponential on Zi. I can introduce Z, where my lambda is positive and my Zi is all this. So my Z is P pseudo inverse lambda, so this term, minus P pseudo inverse transpose 1. Now, since nu is a scalar, I can, pull it till here. So I can write this. So I could write this as minus nu P pseudo inverse transpose 1 vector plus C bar minus 1 vector. And that's my problem that I'm going to solve now on CVX in MATLAB. So let me just set the p-axis to a number, let's say 0.1, just to run this once. And this is my primal. And over here goes the dual, okay? So CVX begin and CVX end. And I'm going to define the variable, which is only the Lagrangian multiplier, that is lambda, and my mu. I'll call it MUU because mu is reserved for CVX. I'll use MUU, and M is actually defined here. So I'll use MW as such. So mu, and I'd want to maximize, as we saw over here, minus nu minus the sum of exponential Zi. So I'll do that. Minus mu minus sum exponential Zi, subject to positivity constraint on L, and we have to define Z as, so I'll call this P pseudo inverse as Pn, and I'll define it just after I define my P, which is here, and it's inverse P transpose times P transpose. This is the pseudo inverse of P. And I'll define my C bar, since we're here, as P pseudo inverse transpose times C. And I'll define a vector of size n by 1, so ON. And I'll define another ones vector, OM, which is of size m by 1. Okay, so going back down here, this guy is P pseudo inverse transpose times lambda. So Z is P pseudo inverse times lambda minus mu, this guy right here. Now we have the P pseudo inverse transpose times 1s, so P inv transpose times ON plus C bar minus OM as such. Okay, now let me solve this. So C is not defined in line 10. Oh, it's because I defined it here. I'm sorry. So I should copy paste this guy here. Let me run this. And I have a mistake. Okay. Run it again. Z is not defined. Oh, it's because this guy should be defined before the function. Okay. Okay, so my dual, actually, my capacity given by the dual function is actually the negation of the optimal value we have. And why is that? It's because over here, we have inverted this just right. This maximize became a minimize because I negated the optimal value. So we should also negate the dual function for that, right? So I'm negating it to get C dual, which is 0.22, where my C primal is 0.53. So here we have weak duality, and the dual is less than the primal. Okay. Now what I think will be interesting is that we plot C primal and C dual on the same plot. I think that would be awesome. So let me remove Px is equal to 0.1. Let me run this and let's wait. And over here in the plotting, let me get rid of this entropy and let me plot on the same one the dual in red and the primal in blue. And let me have a legend. Let me get rid of the Y label and let me have a legend primal and dual. And let me run this. This is what we get. So here's the primal solution, which is the 1 minus entropy, and this is the dual solution, and as you can see, here's the duality gap. Okay, right. One last thing I want to show you is some particular instances where, let's say I want to transmit reliably, instead of 1 bit per second, I want to do so with 2 bits per second. Okay, in that case, I don't have a p-axis. Let me set this to 0 because I'm not going to be using it for just because I'm going to generate an ideal channel. So an identity channel of size 2 power 2 bits. Okay, so doing so, okay, actually let's call this number of bits, define this as 2, and so m and n are 2 power n bits respectively. Get another error. Right, so I'll just perturb, because you get a log 0 and you get an NaN for some values. So this P that I just defined here, let me perturb it by something really small. So my C dual is 1.38 and my C primal is 2 bits. So as you can see, the primal solution is giving you the optimal capacity. So you can transmit 2 bits reliably over this ideal channel. Now you can go up to, let's do 10 bits. See, it's starting to get slow. Actually, let me do 4 bits. So there you go, 4. And so my C dual is 2.77 bits per second, whereas my primal answers to 4 bits per second. So that's it for this lecture. I hope you enjoyed it. We showed you a lot of stuff about capacity, how it could be formulated as a convex optimization problem, as well as its dual, and some use cases or some particular instances for the binary symmetric channels and some ideal channels, right? I hope you enjoyed this video. If you did, please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible.